And welcome back. Today we're going to be looking at fluid dynamics. In other words, what happens to the physical laws as fluids are now in motion? Well, generally speaking, there are three different types of motion. We can have steady flow, unsteady flow, and turbulent flow. Steady flow is when the velocity of fluid particles at any point is constant as time passes. Unsteady flow exists whenever the fluid of the fluid particles at any point changes as time passes. Turbulent flow is an extreme kind of unsteady flow in which the velocity of the fluid particles at a point changes erratically in both magnitude and direction. Fluids can be compressible or incompressible. Most fluids are nearly incompressible. And fluid flow can be viscous, meaning they can have a lot of the particles can have a lot of friction between them, and non-viscous, meaning the particles can have no friction. An incompressible, non-viscous fluid is called an ideal fluid, and that's what we're going to be looking at in our course. When flow is steady, streamlines are used to represent the trajectories of the fluid particles. What are basically streamlines? Streamlines are groups of fluid particles whereby the velocities are the same. When we're talking about fluid motion, it is very, very useful to know how much fluid will basically flow per time. The mass of fluid per second that flows through a tube, it is called the mass flow rate. So, what is the equation of continuity that describes, of course, the mass flow rate? Well, let's see how it was derived. It was derived very simply by using a very common formula that we all know. So, density is of any fluid, really, of any substance, is mass over volume. When we're solving for mass, okay, so it's going to become mass equals density times volume. Now, let's look and analyze volume. Volume is linked with and height. So we can represent now volume by representing it by area times distance. Area times distance, length, width, and obviously height, that's the distance. And looking at it from kinematics point of view, now we can represent distance as velocity and the change of time, because that's what it basically is. So velocity is really the distance and the per unit of change of time. So if we're looking at the mass flow rate, we divide both sides by the change in time, and it crosses out on this side of the equation. So the mass flow rate, which is mass divided by the change of time, is going to be equal now to the density times area times the velocity at that point. So that is how the equation of continuity came about. So let's look at it a little bit more detail. So going back to our PowerPoint presentation, we can see that let's say we have now two sections. We have section 2 and section 1. So as we just saw, the mass flow rate, it is equal to density times area times the velocity by which the particles have. So as you can see, the mass flow rate in both sides has to be equal. So what does that mean? That means that the density times area times velocity of the first section is going to be equal to the density times area of the velocity of the second section. And that's what the equation of continuity basically tells us. The mass flow rate has the same value at every position along the tube that has a single entry and a single exit for the fluid flow. Now, what are the units? That's very, very, very important for the mass flow rate. It is always going to be kilograms per second, because that's how much it's going to flow, because it's really at the end of the day what? Mass divided by time. That's what it basically is. So if we have an incompressible fluid now, we can simply cross out density, because the density is going to stay the same on either side. So the volume flow rate now becomes area times velocity. So let's check this out. Okay, let's say we have the following problem. A garden hose has an unobstructed opening with a cross-sectional area of 2.85 times 10 to the negative 4 meters squared, and it fills a bucket with a volume of 8 times 10 to the negative 3 meters cubed in 30 seconds. So first, we have to find the speed of the water that leaves the hose through an unobstructed opening, and second, we have to find the speed when the obstructed opening it has half as much area. So let's check this out. Let's go back to our sketch pad right over here, and let's solve the following problem. So let's check this out. So we just saw, okay, that the volume flow rate, it's going to be equal to area times volume. So for area times velocity, sorry. So velocity now becomes Q over A. So velocity is Q divided by A, which is area. So how are we going to find out the volume flow rate? So the volume flow rate, they give us the volume, which is going to be 8 times 10 to the negative third meters cubed. And we're going to divide it now by the time, which is, it gave us 30 seconds. So that's how we find Q, the volume flow rate. And we divide this now by the area. The area was given to us as 2.85 times 10 to the negative 4, and it's going to be meters squared. So when we take this number, divide it by 30, and then divide it by 2.85 times 10 to the negative 4th, we see that the velocity at that point is going to be 0.936 meters per second. You can try it on your own and you can see it. So that is our answer for the first part, 0.936 meters per second. Now for the second part, what do we have? Now we have a constriction. So what do we do now? We use the equation for continuity. So area times velocity 1 equals area times velocity 2. And we're trying to find now, okay, the velocity 2. So what does it become? We divide both sides by area 2, just like that. So it crosses out here. So velocity 2 at the second part now becomes area 1 divided by area 2 times velocity 1. So now area 1, of course, is 1. 1 divided by 1/2. So it becomes really just like this times velocity 1, which we got it from here, and we're going to put it under velocity 1 in 0.936 meters per second. So 1 divided by 1/2 is 2 times 0.936 meters per second, and that gives us 1.87 meters per second. And it makes sense. If you really sit and think about it, it makes perfect sense. If you have really the area, you are going to double the speed because these two have an inversely relationship. So as you can see, 0.936 and 1.87, and we go back to our presentation and we check this out. It should be just that. And A is 0.936 and B is 1.87 meters per second. Thank you so much. Thank you for joining me. Bye.